Okay, that was how we use generating functions to solve such combinatorial problems. And at this point, we are going to look at some elementary identities that are useful when we deal with um, generating functions. And we have two identities here that we base these results on. One of them is the binomial theorem, uh, this expression here. Of course, here 1 can be replaced with any other variable like y or some other value, but this is the most useful expression that we make use of in generating functions. And the other one is, which we have seen earlier, the sum of x to the power k, where k ranges from 0 up to infinity, um, is equal to 1 over 1 minus x for some x values, but that is irrelevant for us. And based on these, with a little bit manipulation, we can obtain a number of identities that are useful in constructing generating functions. Obviously, for instance, if your sequence consists of all ones, like 1, 1, 1, 1, dot, 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 etc., up to infinity, your generating function is 1 over 1 minus x due to this identity. And similarly, if it is an alternating sequence like 1 minus 1 plus 1 minus 1 plus 1 minus 1, no, dot, dot, dot. So essentially, this is the sequence minus 1 to the power k, where k starts from 0. Essentially, this is quite similar to what we have here, except for instead of x, you just need minus x to the power k, and essentially this negative x is replaced by a positive x here in this expression. So the corresponding generating function is 1 over 1 plus x. And similarly, if you have something like this, for instance, 1, 3, 9, 27, 81, dot, 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 up to infinity, powers of some number, 3 in this case, and this sequence corresponds to the generating function 1 over 1 minus c times x, and in this case, the corresponding generating function would be 1 over 1 minus 3x. Or if your sequence is 1 only when k is a multiple of some integer m, then your powers will be again multiples of m, and the generating function will be 1 over 1 minus x to the power m. Well, this is simply x to the power m raised to power k, and in this expression, x is replaced by x to the power m here. That's the only difference. So the x here gets replaced by x to the power m. So this is how you obtain such identities. So this is like um, it's 1 0 0 1 0 0 1 0 0 1 dot dot dot. That would be 1 over 1 minus x to the power 3. Okay. Another one is ak equals k plus 1. So this sequence is simply 1 2 3 4 5 6 dot 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 up to infinity, and this is the generating function of this sequence, which can be obtained to be equal to 1 over 1 minus x to the power 2. This can be obtained via the derivative of this expression, which is not that difficult. Another one is where you have a k equal to your sequence equal to this coefficients, and in this case, this is the generalization of this case here. In this case, your generating function is 1 over 1 minus x to the power m. This was 2 here, so this is the special case of this one where m equals 2, but this is the most general case. So there are other identities that you can make use of when constructing generating functions or manipulating them. For those, you can see Rosen, our textbook, or Concrete Mathematics, or that are available in a number of sources. Also, they are available online. If you look up generating functions, you can find all sorts of lists that involves identities similar to this, or some generating function and sequence pairs. Okay, so going back to the coin function, now we have seen that this was the generating function of the well, related to the coin problem, and we just wanted to obtain the coefficient of the term x to the power 50, and for that we just expanded this term while truncating these numbers to fit our agenda. But of course, as we have just seen, at this point we can write this as 1 over 1 minus x, and this one as 1 over 1 minus x to the power 5. This one can be written as 1 over 1 minus x to 10, and so on. So this function is in fact the generating function when we talk about the coin problem. Now, from this, well, it doesn't really look like we can obtain a polynomial out of this, but obviously we skip some details, and in this case, the detail is the convergence of the series, and this, as long as x satisfies certain properties, this is a convergent function, and in fact, it can be written as an infinite degree polynomial. And the easiest way to do that is to actually obtain the Taylor series expansion for this. Now, this is the generating function, and if you just input the Taylor series expansion for this function into Wolfram alpha, it gives you the first couple terms here, 1 plus x squared, etc. You see, the first 5 are 1s, the coefficients, and then it moves on to 2, but I don't see the other terms because it just gives me a big O x to the power 6. Well, we are going to talk about big O notation later on when we discuss complexity. But at this point, what you should understand from this expression is the condition for the convergence of this power series is that actually this x to the power 50 and x to the power 25, x to 10, x to 5, and x itself in magnitude are all strictly less than 1. So it actually confines x to a small interval, and it's close to 0, and which means the powers of x are actually diminishing. If you multiply x by itself, since it's smaller than 1 in magnitude, it gets smaller and smaller. So Wolfram alpha, what it does is it computes a few terms that have small powers, and the rest it just gives you as a big O notation because they become insignificant as the number gets closer to 0. But as you all know, the function, the generating function, its value is irrelevant here. I don't need to compute the value of the function. I just want the coefficient of the term x to the power 50. So click on more terms here, and it gives you more terms. And here you just obtain the coefficient of the term x to the power 50 as 50 as expected.